Okay. Okay. So the next speaker then, Mehul Malik, right?
Mehul Malik, yeah.
Mehul Malik. Okay.
Perfect. Okay, let me just share my slides really quickly.
Please introduce them yourself.
Yeah.
Okay.
Right. Okay, so yeah, so my name is Mehul Malik. I am from Heriot-Watt University in Edinburgh, in Scotland. I'd like to thank the organizers for putting together this event under such difficult circumstances. I wish this were under better, in a better situation, but I hope that it can serve as a platform for helping and advance Ukrainian quantum science. So I want to tell you a bit about the work that we have been doing in my group over the last 5 years or so at Heriot-Watt in Edinburgh, along with a lot of collaborators across Europe. And I want to also emphasize that I welcome collaborations both from experiment and theory in my field. So if you find anything, if you see anything of interest that connects to your research, please do reach out, as we have, I think we have a very nice platform for testing.
Yeah, we see now nothing. Is it okay?
I'm sorry?
We see no presentation now. Is it?
Oh, you don't see it? Oh, I'm sorry. 1 second.
Now it's just black screen. It was.
Yeah, this is because I.
Okay.
But you could hear me, right?
Yeah, and now we see it, but not on the full screen, but better. No, it's.
And now?
Oh, now it's better. Okay.
Okay. Nice. Great. Okay. Yeah. Sorry about that. Right. So as I was saying, so please reach out if you find of anything of interest in my talk. Okay. So my group is called the BBQ Lab. It stands for Beyond Binary Quantum Information, for reasons which will become clearer. We are located in Edinburgh, which is a big city in Scotland. The Heriot-Watt is located a bit outside the city of Edinburgh, which here I'm showing you a picture of Edinburgh. And so there's a lot of space, and it's quite a nice campus. Right, and so I am, of course, also, just like every other quantum group in the world right now, looking for postdocs and PhD students. So if you're able and if you're interested, please do reach out. Just wanted to also highlight, in my favorite bar in Edinburgh has come up with creative ways to raise money for Ukraine, and this was they were selling some shots whose name I will not repeat right now, but they were very good. Okay, so my group works on a variety of different things. We primarily do experimental quantum photonics, and we deal with high dimensional quantum systems, both in space and time. We've recently started working with temporal states of light, and we work a lot with complex scattering media as a platform for manipulating and transporting high dimensional quantum states. I will depart a bit from the previous talks in that I will be talking about discrete variable quantum information as opposed to continuous variable, but there's a sort of a lot of common thread between the two fields, of course. Okay, so what I'll do today is just give you a sort of brief overview of different things that we have done, and hopefully that will give you enough information. Okay, so here's an outline of the talk. First, I will just quickly introduce some high-dimensional concepts. Then I will give you highlights of our platform, which is an experimental platform for generating high-dimensional entanglement, certifying the entanglement, and then showing how it provides enhanced noise robustness as compared to qubits. Then I will tell you a little bit about an experiment where we transported entanglement through a complex medium, and then how we also manipulate high-dimensional quantum states using the platform of a complex medium. Right, so you've heard a few talks already, and as you've seen, quantum sources of light and ways to detect them are fast reaching maturity today. In the last talk, we heard about really beautiful sources of single photons in the form of quantum dots. We have access to very, very good detectors nowadays, which can detect photons with almost near unit detection efficiency. So quantum optical links are seen as sort of interconnects in a global quantum network. The quantum photonics is more than just about QKD. It is about interconnected quantum processors around the world that can be used for many things ranging from information processing to sensing, right? So let me move from qubits to QDITs. So in the discrete variable quantum world, the polarization states of light have played a major role in the last 2 decades, I would say, as a workhorse. So a lot of fundamental quantum experiments have been tested on this platform. However, we all know that quantum states of light in nature can be much more complex. For example, the time degree of freedom and the transverse spatial degree of freedom of a photon can carry many, many quantum levels. We call this a QDIT instead of a qubit for a D-level quantum system, right? And then you can have entanglement in these higher dimensional degrees of freedom. And what's nice is when you go to higher dimensional states, you can get interesting entangled states. So for example, this was a experimental state that we generated in Vienna in the group of Anton Zeilinger, where each photon lived in a different dimensional Hilbert space. So this 332 corresponds to the Schmidt rank of the individual sort of bipartitions of these 3 particle states. So it's different from a G and Z state in the sense that each photon can have a different dimensionality. So the natural question is, besides artistic interest or just curiosity, why do we go to high dimensions? Well, the first obvious answer to this is that as you go to higher dimensions, you can pack more information onto a single photon. So the classical world, people have been doing this for a while, and they have achieved massive increases in information rates through the use of wavelength division multiplexing and space division multiplexing. And so on the bottom, I've plotted sort of landmark results in the QKD quantum com rates that have been also achieved through the use of time frequency. And I foresee that similar jumps will be increased through the use of position momentum encoding. Now, a second slightly more subtle advantage for high dimensional quantum states is that as you increase the dimension of quantum states, they become more robust to noise. So this is an early result from Nicolas Gissin and co-workers that shows that the error rate tolerated by a QKD protocol goes higher and higher as you increase the dimension. So the challenge in this field is really to come up with efficient ways to generate, manipulate, transport, and also measure such quantum states of light. This is not so trivial when you go to higher dimensions, and the tools that exist for qubits are lacking. So this brings me to some of the techniques we've developed in my group. So let's start with the standard source of entanglement, which again, you've heard about today, which is SPDC, spontaneous parametric down conversion in a second order nonlinear crystal. And so normally what happens is you pump the crystal with a higher energy photon, it emits 2 lower energy Signal and Idler photons. And in general, this process is described by phase matching condition, and then this equation here describes what the state looks like in the momentum space, the transverse momentum space given by K, the transverse components of the momentum vectors Ks and Ki, which is Qs, Y, and Qi, Y. So here I'm showing you a plot in 2D, so in the Y axis, but in general, this is a 4-dimensional function that takes on this shape, right? And this function is characterized by some strength of correlation, sigma p, and some bandwidth or size of the modes that are generated that is characterized by sigma s, right? And these parameters strongly depend on how you pump the crystal as well as the crystal length. So the strength of correlation sigma p is dependent on the size of your pump beam omega p. Here I'm just showing you a beam, but it's actually a Gaussian beam being focused into the crystal. And the bandwidth sigma s depends on the length of the crystal as well as the pump wave vector kp. Right? And so I want to show you what the experiments look like in the lab. So this was just the generation part, but actually there's a detection part that plays a big role in what the state looks like, right? So if we look at this setup from the edge on, it's a little bit simpler to see. So the 2 photons are separated by a PBS in this case. So this is second order, type 2 down conversion. And each photon can then be detected by the combination of a device known as a spatial light modulator, or SLM, and a single mode fiber. So what the combination of these 2 devices allows us to do is perform any projective measurement of the spatial mode of a photon. So we can do any coherent projective measurement in any spatial mode basis. that allows us to say, was this photon in mode X or mode Y? And of course, we do this for both photons and then look at coincidences for two photons. And this allows us to sort of query the biphoton state in any higher dimensional basis. So in this paper here, we actually come up with prescribe the full theoretical model for this process, including the collection optics. And we come up with showed a very quick way to measure this joint transverse momentum amplitude function in the continuous degree of freedom. So once you have this joint transverse momentum function, what can you do? So we want to discretize our state into some sort of discrete variable space, which then ideally should approximate a maximally entangled state, right? And this is useful for quantum information protocols, as you heard in the last talk. So what we want to do with this, and a naive first approach would be, let's take our joint transverse momentum amplitude and split it up into chunks, right? And if we can just discretize it into blocks there. And so the hologram on the spatial light modulator for one photon would look like this, which is just composed of discrete pixels spread out. And if we were to make two photon measurements on our state now, so these are showing you coincidence counts between Alice and Bob, you would find that there's a lot of noise or crosstalk, and the state is not particularly flat. There are some bright pixels, there are some not so bright pixels. Now, what we can do is, if we have information about this joint transverse momentum amplitude, we can tailor our basis in a more intelligent way, such that the space between our pixels is chosen according to the strength of the correlation, and the size of our pixels is also chosen such that we approach a maximally entangled state. And now we can then approach a state that looks more sort of flat and is nicely correlated, right? So this is what we did in this work over here in a couple of years ago, where we essentially we call it pixel entanglement, and we show entanglement in these discrete spatial modes of light. So to certify entanglement, you need at least measurements in two bases. So in the signature of entanglement is correlations in at least two complementary observables. So in this case, these are our two bases. One is the pixel basis, which is just simply discrete pixels that we can projectively measure on using our SLM. And the second basis is a mutually unbiased basis composed of a coherent superposition of our pixels with the phase varying in the middle. So this is the higher dimensional equivalent of diagonal anti-diagonal basis or left-right circular basis. What we can do then is make measurements, correlation measurements across the two photons. And this is actual data from the lab showing you that the two photons are strongly anti-correlated in pixel, which is actually transverse momentum anti-correlations. And also strongly anti-correlated in the mutually unbiased basis of pixel MUB, let's call it. And so what we did along with my collaborator Markus Huber in Vienna is we developed an entanglement witness for high dimensional entanglement, which allows us to lower bound the dimensionality of the state and to sort of certify that this state is at least entangled in D dimensions. And then this is without going into too many details. We do this by lower bounding the fidelity of our state to some target state phi in this case. And so using this witness, we were able to certify a certain amount of entanglement back in 2018. However, this was a bit lossy. It took a lot of time because, as you can imagine, scanning through these individual pixels is very lossy, right? So we only kind of post-select on bits of the state. So recently what we developed was we further developed this technique to allow us to use any two MUBs or any two mutually unbiased bases of a high dimensional state to also certify the entanglement. And then we could do this very, very quickly. So here are some results from this most recent experiment. So here I'm showing you correlations in 20 different mutually unbiased bases of a 19-dimensional pixel space. Right? And with this, we were able to certify 18-dimensional entanglement with very high fidelity and very short measurement times. And here is an entanglement of formation, which is an entropic measure of entanglement as opposed to dimensionality. We were able to go up to fairly high dimensions. So for example, this is a pixel hologram that I'm showing you that is designed for 97 pixels. And we were able to certify 55-dimensional entanglement using this hologram. And this work was done by my PhD student, Natalia. Right, so if you add noise to entanglement normally, it's not good. So in the lab, noise appears in the form of, let's say, background counts or detector dark counts. And this would normally show up in the off-diagonal counts where you don't want there to be counts. So for a polarization entangled state, if you start with a fairly pure state, you show fidelity of 92%. If you add some noise in the form of off-diagonal counts in these data matrices, your fidelity goes down. And at some point, it drops below the fidelity threshold, which in this case is 50%. And you're not able to certify any entanglement anymore. Right? So what we showed in this paper, in the theory paper, was that high dimensional entanglement can tolerate a lot more noise than qubit entanglement before you lose all the entanglement. Right? And so if you model your noisy state in this form, where you have some proportion of maximally entangled state and then some proportion of white noise, which can be related to detector dark counts or background light or accidental counts, what we showed was by making measurements in more and more mutually unbiased bases, you can tolerate more and more noise. So for example, if you use, for a 7-dimensionally entangled state, if you use only 2 bases, as I showed you before, for a certain amount of noise P, you cannot certify any entanglement. So here, for example, P equals 0.43, there's no entanglement. But if you use all 8 MUBs of this 7-dimensional entangled state, you can then certify 4-dimensional entanglement by using these more measurements. So it's, in some ways, it's obvious. If the more completely you characterize a state, the more noise tolerant it is. But these are sort of the most efficient ways to characterize the entanglement while still being noise tolerant. So recently in my group, we extended this idea to device independent, so one-sided device independent certification, which is also known as quantum steering, where you can have one party and the channel as well as the source completely untrusted. And then the challenge is, how do you certify the presence of entanglement in this scenario? And this is very interesting for device independent quantum communication protocols, which are sort of the next generation quantum comm protocols. Without, again, going into too much detail, I will show you that we developed a new quantum steering inequality here, where we showed that by using more and more bases, you can essentially tolerate more noise as well as more loss for a loophole-free test of quantum steering. So this is the limit for qubit entanglement in the limit of infinite measurements. So you can make any number of measurements you want on your qubits. Here I'm showing you, if you start using d-dimensional entanglement, for example, going up to 53, you can then tolerate a lot more noise and loss that you just could not possibly tolerate with qubits. And what's even more interesting is that as we go to higher dimensions, the time required to measure this drops dramatically. So in this pink region, we cannot certify any entanglement. However, if you go to 23 dimensions, we were able to certify entanglement. It took us a long time. However, if we increase our dimensionality to 41, we were able to do this within a few minutes. And here you can see that the data is literally just a few clicks. But because we're measuring many, many dimensions, our signal to noise ratio is the same as here. And we're still able to certify or witness quantum steering in this case. This work was done in collaboration with the groups of Nicolas Brunner and Rupe Uola in Geneva. Right, so this brings me to experiment on the transport of entanglement through a complex medium. And what do I mean by complex media? Fog, as you heard in a previous talk, the atmosphere presents a medium where there is naturally lots of scattering. Your skin or your teeth are scattering media. Sugar cube also scatters light. And this is our favorite example, which is a multimode fiber, which also acts as a scattering medium because light going in, the modes mix and they often come out looking like this, where you get a speckle pattern coming through multimode fiber. So let's again start with our very nicely entangled state in 7 dimensions. So this was a state we measured, gave us a fidelity of greater than 94% in this 7-dimensional pixel space. Right? And now what happens when we send one photon of our state through a multimode fiber, right? So the correlations completely go away. There is no entanglement certified. However, what we realize here is this bad data here actually tells us something about the fiber channel itself. And this is a very interesting idea that takes me back to an early concept in quantum information called channel state duality. So some of you may be already familiar with this, but the idea is that if you take a maximally entangled state and you send one particle of this state through some channel T, the resulting state rho captures all the information about the channel. And so this is known as a Choi-Jamelkowski isomorphism, introduced in the 70s. And it essentially says that the statements about the state can be mapped onto statements about the channel. So what this tells us is that the bad data that we measure actually is giving us a snapshot of the transmission matrix of this channel. Now, the parts I have skipped over is that this transmission matrix in general is a complex value transmission matrix. And we need to measure the relative phases of all the elements, all the rows and columns. And that part is done through techniques involving interference and a phase reference, which I don't have time to go into. Now, once we measure the transmission matrix, what we can do is construct a new basis where the entanglement is still there. So the entanglement is going through a unitary channel, in this case, close to unitary channel T. It doesn't go anywhere, it just gets rotated in a weird way. And what we are able to do is find a basis where the entanglement still exists, but we only need to do the rotation on one side, on Alice's side. So on Bob's side, we don't do anything. We measure in the same basis as before. We don't touch the fiber. And now this was the data before we do this. And when we have this new scrambled basis on Alice's side, we get our correlations back. So in order to certify entanglement, we of course need to measure more than in one basis. And so we were able to then find 7 other mutually unbiased bases where we are able to regain the correlations. And with this, we can certify a fidelity of 84% to the 7-dim entangled state and certify that we have 6-dimensional entanglement transported through the fiber. Good. So this was a work led by my students, Natalia and Suraj. Suraj was actually visiting our group for a summer back then. Right, so finally, this brings me to the last part of my talk, which is how do we manipulate high-dimensional quantum states of light? Right, so you're probably all familiar with this idea of photonic integrated circuits. These are made up of building blocks of Mach-Zehnder interferometers, phase shifters, beam splitters. This is kind of the workhorse in photonic information processing. However, what the problem with this method is that the number of components you need as you increase the dimension of the state grows quadratically. And any errors that exist in the fabrication or the control of these elements propagates drastically. Now, what we in this recent work, we proposed a different way to manipulate quantum states using this inherent random mixing that exists in a complex medium. And what we do is we embed our circuit in a larger dimensional space composed of some big ambient mode mixer U, sandwiched between some phase planes P. And this, what allows us to do is take the control outside outside the circuits to these single phase planes. And then these mode mixers act as a free resource, which allows us to sort of use the random mixing as a resource, additional resource. So in a previous part of my talk, I was telling you about this 7-dimensional state inside the fiber, but actually the fiber is much bigger than 7-dimensional, right? The multimode fiber can support hundreds to thousands of modes. So in this case, our fiber supports 200 modes for one polarization. And so in this experiment, what we did was we used this higher dimensional space. So scattering into this higher dimensional space as an additional resource, which allowed us to program any unitary circuit for certain dimensions inside our multimode fiber by the use of these 2 SLMs before and after the multimode fiber. So this is example data of unitary operations of gates, high dimensional quantum gates that we implemented. This is, of course, identity. This is the Z gate. This is the X gate. These are all 5-dimensional gates, and this is the discrete Fourier transform in 5 dimensions. and this is a random unitary. So this is data, process tomography data. This is process tomography matrices, process matrices reconstructed with these fidelities. So as you can see, the fidelity is not great for higher dimensions, and this is because we only have 2 planes and we have a certain size of fiber. In this paper, we also generalize this to n planes and then also increase the dimensionality of the fiber to show that this allows us to actually perform unit fidelity operations with no loss. Right. So this work was led by my postdoc Sarosh and my student Suraj. Okay, to summarize, I'll just kind of put this out there. I talked about the generation of entanglement, high dimensional entanglement, and its certification. Showed you how high dimensional entanglement is very noise robust and allows you to even tolerate massive amounts of loss in device independent certification of entanglement. I talked about the transport of entanglement through a multimode fiber, as well as how we can program general unitaries for high dimensional quantum states inside these multimode fibers. I want to advertise a different kind of paper very quickly that I wrote recently on the mobility of quantum researchers. And I think now is more than ever the right time to talk about this. And so in this paper, me along with some colleagues, we highlight sort of problems or hurdles, let's say, that stop the mobility of researchers in our field, actually any field for that matter. And we propose solutions based on examples of good practice from around the world that governments, institutions, and PIs can do. So I encourage you to take a look at this. And that finally brings me to my last slide, where I'd like to thank you for your attention, as well as my collaborators around Europe. So happy to answer any questions. Thank you.
Thank you very much. The talk is open for questions. When people are thinking, I could not say that it is very clear for me in details, but actually I didn't understand 2 things, especially. If fiber is so much more dimensional than 7, let's say, yeah, then how could you recover the signal based on the data from 7-dimension detector?
Right. So that's a good question, actually. So in this experiment, right, the light that was entering the fiber, so some of it, of course, was lost to the higher order modes. But in this case, the fiber is just sitting in the lab. It wasn't bent in a very, very strong way. And what we found was a lot of the light stayed in these lower order modes that we were exciting. So in a multimode fiber, if you excite the very center of a fiber, if you launch a Gaussian mode, actually what comes out is not so far away from a Gaussian spot. If you excite a higher order mode of the multimode fiber, you get this speckle. Or if you bend the fiber very strongly,
like
you get
higher harmonics, right? Okay.
I'm sorry?
Like higher harmonics.
Yeah, exactly. Okay. Yeah, so it's very close to like a nearly aligned cavity, for example. So yeah, so in this case, we were of course post-selecting on these seven lower dimensional modes of the fiber. But actually, in the next experiment, then we excited all the modes of the fiber.
But I didn't understand when you mentioned that it was time-consuming to scan all the channels of the detector. But then you said you use a trick. That I didn't understand. What was the trick?
Right. So the time-consuming part there was had to do with the fact that So the fact that when you measure in a spatially localized basis, right, like a pixel basis, where you have to scan through individual small discrete modes, and this is lossy. So therefore, you need to measure longer to have some good statistics. The trick was that we don't need to measure in this basis. So all the previous sort of witnesses constructed for some computational Schmidt basis of the state. But actually what we showed was we can use any 2 bases. So if we can use a basis, so this d-dimensional space in general has d+1 bases for prime dimensions. We can use any 2 mutually unbiased bases, which allows us to do high photon flux bases where you're sort of exciting all the modes.
Mhm. Okay. Okay, thank you. I see Andrei has a question.
Yeah, I have questions. Thank you. I have such questions. So when you light is actually more infinite dimensional system, and exactly on this slide that you now think I have a question that you have some restriction. Did I understand correctly to this Hilbert space? And so far as understood, this restriction, when you do this restriction, you may say that presence or absence some correlation, for example, entanglement for the dimensionality, assuming such a restriction. Can it be that some artifacts may appear due to such restriction? Because I know when we restrict, for example, this a little bit different story, of course, but when we restrict photon numbers, some artifacts do appear.
Yeah, so you're absolutely right. There are definitely some artifacts that appear. So do you mean, so firstly, do you mean that the dimensionality in general is infinite?
Yeah, generally it's infinite. For example, light is not entangled, but due to restriction of Hilbert space, artificial restriction of Hilbert space, you see that this is entangled, for example. Can it be or not, this entanglement?
Well, also the first restriction that is imposed is just by the experimental apparatus itself, right? So we have finite apertures in the setups, which truncate our state. So in general, yes, you're right. When we write the state, it's Gaussian, it's huge, right? But so if the first restriction is imposed by the physical apparatus itself, in the theory, I think this is not the case. So there's one measure is the number of modes in the system, and the other is the number of entangled modes in the system, right? The number of correlated modes in the system, and these are not infinite simply because you have a certain finite number of correlated modes or entangled modes, right? And this is
okay.
Yeah,
I get this difference. Yeah.
So the Schmidt decomposition of your continuous infinite dimensional state will give you some finite dimension.
Okay, thank you very much. Yeah, I see.
Okay, more questions? Then we thank the speaker. Thank you very much for very interesting talk, very complicated as for me.